Okay. So we are going to start 12.6 today. And I wanted to do a quick little recap, real quick. When it comes to our different coordinate systems, we have in two-dimensional space, we have two coordinate systems that we like to use. They are Cartesian, which is what we've been doing our whole lives, x-coordinate, y-coordinate. And then we have what we talked about a couple of days ago, polar coordinates. And that's just another way to get around if you're on a flat sheet of paper. So as a quick reminder, bless you, if we are in two-dimensional space, if I want to get to some point in two-dimensional space, if I do Cartesian, then what I'm going to do is I'm going to start here at the origin. I'm going to go out a certain distance and a certain distance up, right? The certain distance that we go out will be x, certain distance we go up is y, right? Now, if we do polar, same thing. We start at the origin, but we imagine that, just kind of imagine we're looking from the top down, that you're just a person standing here, right? And you're looking out the x-axis. Somebody's going to give you r and theta. So theta is going to tell you how much to rotate by, and then r is going to tell you how far out to walk, right? So that's Cartesian and polar. Are we all clear on those two? But in three-dimensional space, we have three coordinate systems that we like to use. Cartesian, which is, again, what we're used to, right? Someone gives you a point in three-dimensional space. Of course, it's going to be harder to read or visualize this, but somebody gives you some point, some x, y, z. The x tells you how far to go out here. Then the y would give you this, that distance, which would be along the y-axis or parallel to the y-axis. Then z would tell you, up or down, so maybe we go to there. So maybe that's our point, right? So that's one way to get to that point. Another way we could have gotten to that point is to use polar. Use polar to get us to this point, the one on the ground. So imagine you're standing at the origin, right? And again, we're going to act like we're a person standing here. We're looking down the x-axis, and I could walk out x, then go y, then go z, or someone could tell me how much to turn by. So I'm going to use I'm going to try and stay on camera. Let's say this is the x-axis, y-axis, and z, right? So let's say I'm trying to get to that vent right there, okay? So I'm trying to get to that vent. I could go, walk out x, then go y, and then go up z, right? Or polar would be, instead of me going out x and then y, somebody telling me theta, right? Then r, that's just like polar, right? But now, how do I get up there? Well, just give me z, and that'll tell me, how far up or down to go. So in three-dimensional space, polar becomes what we call cylindrical. And so your x is the same as it was in polar. Someone's gonna have to give you r and theta, right? And the y will be r sine theta, so someone gave you the theta and the r. But the z is just z. It's just whatever, it's just some number, okay? So do y'all see that it's just polar in 3D? Now, why do they call it cylindrical? Why do they call it cylindrical? Yeah, how can we visualize that this is a cylinder? So I would like for us to just right now consider cylindrical coordinates. That's where we are here, okay? Okay, so I brought some fun stuff to play with today. And I'm going to need a volunteer, and I'm not going to make the volunteer get on camera. This thing looks really dirty. It's not that dirty, but I'm going to have someone hold it. Who wants to volunteer to hold the other end of this? Chris? All right, thank you, Chris. Appreciate that. So I'm going to be here, let's go back to this being the x-axis, y-axis, right, and z. So you are going to hold this end, right? Okay, you can move back a little bit. Right, that's fine. Okay, so in cylindrical coordinates, someone is supposed to give me theta, right? Theta, what else? R and Z. Okay, so first, I'm going to draw this back. I'll hand it back to you in a second. First, here we are at the origin, right? All right, somebody give me an R, right? So someone gives me the number 2, whatever. So we go out, right? So there you are. Okay, now someone gives us a theta. So what, maybe like pi over 3 or something. So now what? Go this way, right? Let's just go a little further so everyone can see me, right? And then Z will be up or down from here, right? So what I want you to do, all right, is I want you, everyone just keep a eye on his hand, all right? So if I hold this radius constant right now, I want you to change Z up and down, okay? So we're both going to go up and down. So what is he drawing when he goes up and down with Z? What is that drawing? If he goes up and I go up,
A rectangle.
just his hand is just a straight line going up and down, isn't it, right? A straight line? Do y'all see that? Okay, so imagine we're going to go up and down again. Up and down, right? But now I want you to also, let's vary our radius like this at the same time. So go ahead and go up and down, move a little bit, up and down, move a little bit, up and down, move a little bit. Do y'all see what he's drawing? A bunch of lines that are all the same radius, aren't they? Which would create a cylinder, right? Now if I let him out a little more, right, like that, and we do the same thing, he goes around, goes up and down, up and down. It's just a cylinder with a bigger radius, right? Okay, you're good, thank you. Great job. It's like it seems like you've done that before or something, huh? So I have kind of a visual for that. So if we're looking from the top down, so right now we're looking at the XY axis, then we already know that we can change the radius, we can change the theta, and that will swing us around. That's polar, but we have to imagine that we're now in 3-dimensional space, right, instead of 2. And so as I let my Z go up and down like that, that's what I was trying to get Chris to do, right? And then as I change my theta and go around like this, all those lines get swung around. Then you create this cylindrical shape. All right? So do y'all like this picture better or Chris? Chris was better? Good job, Chris. Okay, so we can do things in Cartesian or we can do things in cylindrical coordinates. Make sense? My professor, when I was in Cal, well, when I took calculus, I took 4 classes. I took Cal 1, 2, 3, and 4, but they were all 3 credit hours, not 4 credit hours. So it was still 12 total hours, right? But I did 3, 3, 3, 3. So I did this in Cal 4, and my professor liked to drink. So he called this, whenever we're in cylindrical coordinates, he called it Planet Schlitz. I guess Schlitz is a beer or something. I don't know. Has anyone ever heard of Schlitz beer? They think it's a beer, so he would call it Planet Schlitz because it looks like a beer can or something like that. It's always stuck with me. So when we're in cylindrical, we're on Planet Schlitz, all right? So now that we've somewhat established what the coordinate system is, how is it that we are going to be able to use these to do triple integrals? Because that's what this chapter is about, or this, well, not this chapter, this part of the chapter. So when we're looking at a triple integral and we're trying to look at the region of integration, right, that E, that solid, then if we are in cylindrical coordinates, what will it look like if our theta varies between 2 constants, right? So that means this can be like this, between 2 constants. Our radius is between 2 functions of theta, so how far I go out, right, is going to be between 2 things. And then how far I go up, that's my Z, is between 2. Now these are functions of 2 variables. Do you see we're calling it U1 and U2. This is really X and Y, isn't it? X, Y, and this is This is some function of x and y. So aren't these two surfaces, right? So what we get is a region that looks like this. So we have this three-dimensional solid where when you look at the shadow of the solid onto the ground, you get that polar rectangle. Remember, we call this a polar rectangle. So we have a polar rectangle on the ground, and then we have a top surface up here, and then we have below it, we have some bottom surface like that. So this is very good. This is a very good coordinate system to use if the shadow on the ground is a polar region, right? And we did this last class, didn't we? At the very end, we proved that the volume of a sphere is 4/3 pi r cubed. And when we looked at the shadow on the ground, it was a circle, so we converted to polar. I told you we're actually getting into this section, and this is why. Okay? Everyone sees your theta is between two constants, right? The angle that you're sweeping through is between two constants. Your r is between, your radius is between two functions of theta, and then your surfaces are those two, top and bottom. Okay, so let's see what the triple integral looks like. So the triple integral will have to be set up in the correct order. You integrate, your outer integral is going to go alpha beta. Your middle integral is the functions of theta. And then your inner integral are your two surfaces. And then this piece right here is the function we're integrating, which, remember, E is only the solid, right? We're integrating a function that lives in four-dimensional space. So this is that function we're integrating. And then I have it here, don't forget the r, but that r right there, right, is very important. That r has to be placed into the integral because you went to polar, right? Now I'm going to talk about this r in much more detail today, all right, if we can get to it. And then you go integrate with respect to z, then r, then theta. So let's do a problem. So we want to find the triple integral over E. We're integrating the function x. Pretty boring function, right? Just x. With respect to volume, if E is the region bounded by all that stuff. So z equals 0 is the ground, right? That's the xy plane. What is this? It's a plane. So imagine we have the ground, and then we have some plane, right? Some plane. And then we have two cylinders. Both cylinders open which direction?
Upwards.
Upwards, like up parallel to the z-axis, because both of these equations don't have z. So z is a free variable here. So we have a cylinder that has a radius of 2 and a cylinder that has a radius of 3. So can you see like a beer can with the beer can on the outside of it, right? Or Coke can, whatever you prefer, or water, whatever you like, okay? So we have two vertical cylinders like this. We have one that's a little bigger than it like that. And of course these go forever, right? But we have the ground coming through, right? The ground is going to come through and cut the bottom off, right? So we have a bottom. And then what's cutting the top of it off?
Plane.
The plane, right? So the plane's going to come through here and somehow slice through this thing like that. And so we're trying to, the solid we're integrating over, right? The solid E, that region of integration, is the solid bounded by all these. So there's like a three-dimensional solid in here. Do you all see it? I'm going to try and draw it. It's going to have a little angle to it, like this, and come down like this. Do you all see something like that? I'm not quite sure of the tilt of the plane. I don't really care, because that would depend on your perspective point. But the ground cutting through, a plane cutting through, and then the region between the two cylinders. So we're talking about, all this, all that in there, and there's a hole inside the sushi, but cut at an angle, okay? So it's hollow inside, right? There's nothing in there. That is E. So if we look at E and we project it down to the xy plane and take a look at the shadow, can you all see what the shadow of that would look like? Yeah, so you would have in two-dimensional space in the xy axes, or x with the xy axes, you would have two circles, right? Bigger one and a smaller one, like that. And so the shadow would be this piece right here. And this would be, what was it, 3 here, and then that inner one there is 2. So isn't that shadow a really nice polar region? It is a good polar region. How could I set up my restrictions on theta and r to create that polar region? So 0 to 2 pi, that would swing me all the way around. But I want my radius to be between 2 and 3, right? I don't want this stuff in the middle. I just want from 2 to 3 out. So radius between 2 and 3. And then the last thing we need to do is determine what our restrictions on z are. So then we go back to this, and we look and say, what's the top surface and bottom surface? So what was this top surface here?
The plane.
That was the plane equation. And we're going to solve it for z. It will be z equals x plus y plus 5, so it was already solved for z. And then the bottom of this thing is z equals 0. Okay? We all right with that? So it looks like we would put here 0, right? And then here x plus y plus 5, right? But we've gone to polar. We've gone to Cartesian. We're in Cartesian. Cartesian really means polar. So we have to replace all of our x's with what? R cosine theta, and all our y's with r sine theta. So when I set these restrictions, I'm going to go 0 here, but I'm not going to go x plus y plus 5. I'm going to say r cosine theta plus r sine theta plus 5. You all see that? Okay. So we've established what the region of integration looks like. We have defined that region of integration by setting up the bounds on theta, r, and z. And now we need to actually set up the triple integral. So we're trying to do this triple integral right here. So I start writing it down. I'm going to go 1, 2, 3. Okay. We'll put the limits of integration on that in a second. What are we actually integrating? What's in here? X, but we've gone to polar, cylindrical, so really this should be r cosine theta, right? Right, that should be r cosine theta, that should be x. And then what? Times r, right? Times r. So we have to multiply by times r because we went to polar, we're in cylindrical. And then we integrate first with respect to what? Z. Okay, z never changes, okay, in cylindrical. Z is always just z. And then d r, then d theta. And then over here, 0 to 2 pi, 2 to 3. And then look at our nasty limits of integration on the inner integral. 0 to r cosine theta plus r sine theta plus 5. Now, just to be clear, I want to make sure you understand something here. What if we were integrating the function, and what if the function here was z instead of x? What would we put here? Just z. Because z doesn't change to anything. Yeah, zr, sorry, zr, the r would still be there. But this thing would just be z, because in cylindrical, z always just stays z. All right? The only thing that ever switches is the x and the y. So that's not what we had. If this were y, then that would be r sine theta times r. All right? So now we have the pleasure of trying to integrate that. And this is just tedious work at this point. I'm going to change this to r squared. Get rid of that r. Okay, let's do the inner integral first. Pardon me? Yeah, since we're doing it with respect to z, we treat all of this like a constant because there is no z here, right? So the antiderivative of that with respect to z is r squared cosine theta. We're going to evaluate that can put this in brackets. We're gonna evaluate that. dr d theta. So where are we evaluating? From what to what? From z, I forgot the z, didn't I? Oops, sorry. Z. From z equals 0 to z equals all of that, right? R cosine theta plus r sine theta plus 5. So the good news is that when we plug in 0, right, it's nothing, right? This one going in kills everything off. So all I really have to do is rewrite this with that being that, right? Okay. Integral 0 to pi, 2 to 3. And then, so the way I'm going to look at it is I'm going to take r squared cosine theta and distribute it through to each of these. Is that all right? Because that's what's going to happen. So what do we get? Our first term would be r cubed cosine squared theta. Then r cubed again. Cosine theta, sine theta. And then the last term should be plus 5 r squared cosine theta. All right, dr d theta. So now I integrate with, yes,
Could we have simplified the cosine plus sine earlier and just made that 1 before we...
It's not squared.
Oh.
Yeah, they're not squared. Had they been squared, oh, absolutely, I would have loved to have seen that, but yeah. So now we do the antiderivative of this with respect to r. So all the cosines and sines are all constants. So let's see here. Integral 0 to 2 pi. Okay, here comes my antiderivative. 1/4 cosine squared theta. Yeah, well, I don't know what about it. I don't know what happened to it. 1/4 r to the 4th cosine squared theta. I'm just having a really off couple of weeks.
Are you in Taurus? Because that might be it.
No. I forgot again. I keep making excuses for it. I think I'm mentally tired. I tell you all, my dad was in the hospital. He had surgery, and it's just been very stressful. He's better, yeah. He's actually back at home, so, you know, but it's just been a lot. Okay, y'all double check. I got that right? Look okay. And then r is 2 and r is 3. I wish that r was 0. D theta at the end of that. So you got to plug in 3, and then you got to plug in 2. Okay, so can we just leave that alone? Can I just ... this? I do want to talk about, after you do that next step, okay? You will have to do integration with respect to theta, won't you? Yes? So let's just talk about what would happen. I mean, like when I put a 3 in here and a 2 in here, I'm going to wind up with a number out there at some point, right? So if you had to integrate that part when you get to it, how do we integrate cosine squared? Yeah, the reduction formula, so you'd use that thing, it's like 1/2 and then like 1 plus cosine 2 theta, something like that. That's the formula for power. It's power reducing or reduction or per half angle. It's called different things, but this is back from Cal 2. And then this one right here is a basic u sub, because if you let u be sine, the derivative is cosine. So that's just like a basic u sub. And then that one's just antiderivative cosine. So you think you get that? Let's just see what the answer is. I think I did have the computer do this already for me. Oh, well, I never showed you the region. There it is. There's everything. And if I put the solid there and take everything out. Why is my computer? Oh, there it goes. Yeah. So there's the region that we are integrating over. Remember, we didn't find the volume of that, right? That's not what we did. That was just our region of integration. Okay, yeah, so there's the work for it. It all comes out at the end of the day to be 65 pi over 4. All right? All right, let's look at another one. There's only 2 examples in this section, then we're moving on. Okay, find the volume of the solid between the 2 cylinders, x squared plus y squared equals 4, and x squared plus y squared equals 16, which also lies within the sphere x squared plus y squared plus z squared equals 36. I wish that wasn't there because that kind of gives it away already. But we're trying to find the volume of a solid that is the volume between these 2 cylinders. So again, that's like the beer cans, right? It's between those 2, right? But those 2 go infinitely, so we need some other restriction. So then what we do is we wrap it with a sphere. And so you get that picture, and if we take everything out, it would look like this. Y'all see it? That is the region between 2 cylinders, between the 2 cylinders, but also within some sphere. All right. Now this is a little weird because this picture is both above and below the XY plane, right? The XY plane. It's above and below. So when we talk about a shadow, you kind of have to imagine that maybe you like lift this thing up and off the plane so you can still see what the shadow is on the ground. What would the shadow be? This. Very much like what we just had, right? You're going to have something like this. You're going to have 2 circles like that, right? So that's our region of integration on the ground. And what's our radii here? 2 and 4. Okay, so we've got this as a polar region, no problem. 2 pi, 0, 2 pi on the theta, 2 to 4 on the r. Now we need to find some control of z. Okay, so how are we going to control z?
You do like the top would be the circle.
Yeah, so the top of this thing, right? The top surface is the upper half of the sphere, right?
And you could do 0 at the bottom and then multiply by 2.
Okay, so since we're asking this, okay, let's think through this because this is super important. I think what you're suggesting is we use some of the symmetry here, right? The symmetry that the top half and bottom half of these look the same. The question is asking for the volume. So we can do that. But I just want to be careful here. If this was asking you to do some triple integral here, right? If this was asking for you to do some triple integral of, let's say, like xy plus z squared with respect to volume, then it would be very dangerous to break it up into 2 pieces. Because even though the region of integration is symmetric, top and bottom, what this is doing within each of those 2 regions may not be the same. Does that make any sense? So, like if you picked a value, pick an x, y, z, like pick a point up here. If you go the same thing but go down, what the value of this function at this point is not necessarily the same value as this point. And so this triple integral over that solid may not have the symmetric properties. But because we're not doing this, what are we doing? What are we integrating then? We're integrating 1. See, the function we're going to use is 1, and that's the formula from last class that, well, was it the last class? I don't remember. If you do yeah, it had to have been. The triple integral over E of 1 dV is equal to the volume of E. That's how we prove the volume of a sphere, or a solid, a ball, whatever. This is the volume of E. Okay? Just like the double integral over d of 1 with respect to area is the area of D. The triple integral of 1 over E is the volume of E. So that's what we're going to use here. And because of that, we can use the symmetry. Okay? So what we're going to do, just remember, we have to double the answer. The bottom of this is the bottom surface, is we're cutting this through with the xy plane. All right? That's the bottom of this. The top of it is what? This sphere, but how do we write it? Yeah, we have to actually take this and solve it for z, right? What would this be solved for z?
C is equal to b square root of 36 minus x minus.
Right, like that. Now, it's supposed to be plus or minus, but I'm only taking the plus because I'm only looking at the top part of the sphere, right? If I wanted the minus, then I would have to do the other side, right? Which is what you would have to do if this wasn't 1. Okay, if this wasn't 1, the top would be positive root 36 minus x squared minus y squared. The bottom would be negative root 36 minus x squared minus y squared. All right, those would be your two surfaces. All right, so what am I going to put here then? Square root of 36 minus r squared. Good. So where do we get the r squared from? Yeah, we just pull the negative out of both of those and then recognize that x squared plus y squared is r squared. That's part of what we knew when we went to polar. All right? All right, let's go ahead and set this triple integral up. See if we have anything that looks intimidating, and then we'll just leave it to our, we'll leave it to you to go work it out later if it doesn't look like it has any real big issues. All right, so we are going to do the triple integral over E of 1 dv, which is going to be the triple integral, let's see, 0 to 2 pi, 2 to 4, 0 to root 36 minus r squared. And then what are we integrating? 1. Which is really going to be what for us, though? R. We have to have the r in there still. So even though it's 1, because we switched over to cylindrical, or polar if you like, we still must include the r. Let's just do the inner one, okay? And then I think after we get past the inner one, the rest of it's pretty straightforward. Okay, so integral 0 to 2 pi, integral 2 to 4. The antiderivative of r with respect to z is rz, right? And we're going to evaluate that from z equals 0 to z equals root 36 minus r squared. Hey, I don't know how y'all want to do this. Do you want to remember that we need to double this, or do you just want to put a 2 out front? I mean, it's up to you, okay? We should probably put 2 out here because this, we need, if we're going to say that this is equal to this, we need to double that answer, okay? Now let's put the 2 out there. And then when you do this, you plug this in for z, and then you plug 0 in, it'll kill it off. So I think the next double integral here, right here, is I think where we can stop. Because we're going to have r times square root 36 minus r squared dr d theta. Right? That's what we get? Yes?
So could you please go back over whenever
Yes.
you mentioned that you can't always just multiply what we get by 2? Like say because remember you said that wouldn't always work, splitting the volume into 2 and then like multiplying. What was the reasoning behind that again? Like,
Okay, I'll give you an example that goes back to Cal 2, all right? Yeah, so let's say I'm trying to find the area, back in Cal 2. Let's say I'm trying to find the area between 0 and 1 of some graph right here, right? All right. Or let's say I'm trying to find from -1 to 1. From -1 to 1. Or I'm trying to find the area under here. Can you just find the area from 0 to 1 of this function and then just double the answer? No, because what you would have to have is that the other side of this would have to be exactly symmetric. Like there would have to be symmetry here, right? This right here would have to be symmetric over the origin in order for you to use this property of doubling, all right? So in this problem, we are asked to find the volume, right? And we're asked to find the volume. That means the function we're integrating is 1. So that is constant, right? It's symmetric everywhere. Like you plug anything in, this thing just spits out 1. So it doesn't matter where you are, it's just going to spit 1 out, right?
Okay.
So when you look at that, thing we had, that little shape thing we had, right, like this, it doesn't matter where you are on this little solid. When you plug in any point, you're going to get 1. So why don't we just cut it in half and then plug in the top half? And because of the symmetry of this piece, whatever happens with that point also happens with the point on the bottom, right? Because it's always going to be
But what about the
1.
top half, like the top part, the little dome?
Doesn't matter.
No?
Doesn't matter because the function is 1, right? It's like, you know, there's a,
Think of it like density, like charge. Like if that function is the density function or the charge function,
okay, maybe that'll be a better
and
example.
like change as you go throughout the whole entire volume.
I like that. I like that. Let's use that. Let's say that we're trying to find the mass of this thing, okay? The mass of this. And I tell you that at every point, the density is always the same. It's uniform, it's homogeneous, okay? Then what you could do is you could find just the mass of the top half and double it. Do you agree? Take them, if you could find the mass of that top half.
Well, that's assuming that it's half, right?
What do you mean?
Because the bottom is like a can, it's just a regular cylinder, but then the top is the cylinder.
No, the bottom is curved at the bottom also, like this.
Oh, it is?
Yes, because it was made by a sphere.
Oh, I thought that there was like a plane cut.
No, we cut it in half, and we're doubling the answer.
All right, I'm fine now.
You sure?
Yeah.
Okay. But I like that example. If the density of this object at every point is uniform or constant, then finding the mass of the top half and doubling it is fine. But if the density of this thing is non-homogeneous, non-uniform, so densities at different points are different densities, then you can't just take the top half and double it. You have to actually move through and look at the whole region itself, unless the density function is symmetric. If, like, an example of a density function that would be symmetric here would be something like if our density function would be something like x squared. Let's see, x squared. So all that matters is your x coordinate, right? So like if you just pick an x coordinate, whatever it is, square it, that's the density there, then whatever happens up here is the same as what happens down here. So you would have the same density no matter what. But I like that. I'm going to use that from now on. I've been doing this for a long time. But then again, I don't think I've ever had a class start talking too much about this aspect of it. Anyway, I like it. Good. All right, where were we? Here, right? So, could you do that integral? This right here? How? Basic u sub. It's just a basic u sub. Take that right there as your u. The derivative of that is almost that. So you're off by a constant. You'll be able to get it. And the answer to this, well, it's a really nasty answer. If you leave it in the exact form, it's like a 512 root 2 times pi over 3 minus 160 root 5 pi over 3. But if you go to a decimal, it comes out to 383.595. That would be the volume of that solid. cubic inches, cubic feet, cubic whatever.
And that's already multiplying it by 2?
Did I multiply this one by 2? Hold on. I think I see a 2 in here. I see a 2 in here. Let me scroll up. Uh-oh.
I see it too right there.
Yeah, but I typed the way I typed it in. Hold on.
There's the 2 right there on the
You did the
2r
top and bottom.
square root of.
No, but that's that has to do with the antiderivative.
Because you set your limits of integration to the negative and positive.
Oh, I did the whole thing. Okay, see, all right, so we didn't, yeah, remember I said, do we want to use the symmetry or not? Okay, on this one, I did not use the symmetry. So that's a kind of an interesting, what would happen if I come in here and change this to 0? Come on. 0. And then put a 2 out here. 383.595. So you get the same answer. Yeah. Okay. All right. So the homework problems, there's only 3 of them there. Okay, it's just to practice using cylindrical coordinates. Cylindrical, I think, is pretty well, I'm not going to say pretty straightforward, but it's just an extension of polar, right? It's an extension of polar. All right, so we move on. Spherical. All right, do we have any new volunteers for spherical? Or did you really like Chris's volunteering? You don't want to see Chris again? Chris. All right, so same thing. We have a third coordinate system in 3-dimensional space. We all know Cartesian, right? We were born and raised on it. Cylindrical, we've now talked about. But now let's go to this idea of spherical. So here's the way it's going to work, and this can be a little weird, Chris. I'm not quite sure how we're going to do this. All right. So let's imagine again that I want to let's just say I want to try and get to the projector from here. X-axis, Y-axis, Z-axis. I'm still going to need 3 pieces of information. X, Y, Z, or we could do R, theta, Z, right? That's 3 pieces of information. But this time, the 3 pieces of information I'm going to give you are first, I'm going to give you this thing called rho, which is the Greek letter R, which is still going to mean radius, okay? So I'm going to give us a rho, a radius. Then I'm going to give you 2 angles. All right, 2 angles. So here's how this is going to work. Chris, I'm going to have to be down here at the origin, all right? I'm actually going to have to come down here at the origin, all right? So you know how we normally sit here and we face out the x-axis? We've always been doing that? Okay, this time, okay, go ahead. I'm going to be sitting here looking up, all right? I know this is strange, but I'm like this way and looking up. Okay, so bring this rope right above me if you could. All right, so now I'm going to give us an angle. First angle is called phi or phi. People call it, okay? Y'all like phi or phi? Doesn't matter, I'm going to just say both, interchange them. So the first angle is phi. Here it comes. So start rotating down. There's phi. Go ahead and keep going a little bit so you don't have to hold it so high. That's your first angle. Now your second angle is theta, which is now what it was back in cylindrical. This one, okay? Phi, come down a little more. Okay, now rho. So go ahead, Chris, take me to the projector. You see? You got to get to the projector though, Chris. Oh, you might actually, you're tall. But you see that? Rho is like radius, but now I've got the 2 angles. Okay, so let's come back. Rho, come back in. All right, small rho here. And then let's go theta back to 0 and phi back to 0. Understand? Okay, thank you, Chris. Excellent job. Excellent job. Okay, that's a totally different way to get to that point, right? You know what? Hold on, Chris. I think we need more. Because we don't know why we call it spherical yet. Here, but this time I won't sit down. We'll just do it right here. Okay, so imagine right here, this is the origin, okay? This is the origin, everyone? So let's start where we always start, which is we're going to face out this way with phi being 0. All right, so go ahead and give me a phi. Okay, and then go ahead and give me a theta. All right, let's just come over here some more. Okay, and now what I want you to do is I want you to vary phi. I want you to move, like let phi change. Yep, and what is he making when he does that? He's making a little curve, isn't he? Like this, a little curve. Because see, I'm not moving, I'm staying here. He's making a little arc. Now, do that and also change theta. Okay, so what is he making when he does that? It's kind of like part of a patch on a sphere, isn't it? Because it's curved. Thank you. God, outstanding. Do y'all see that little patch? It's curved, right? So if we were to see this, I think Chris is so much better than this picture. Right? I think he's better. So phi is that angle from the z-axis straight up pointing down. Theta swings you around. And then, of course, you can change your radius, which is rho. So if you do that, you're going to get that little patch out there. You see that little red patch out there? Right? Get that little patch. And that little patch, it's like, when I was thinking about how this class would work, I was thinking of me coming in here and like doing something like this. This is going to get dangerous. Watch out. Okay? Watch out. Everyone watch out. Imagine that I'm sitting here and I'm swinging this thing around. I better make sure it's really connected here. Good. Okay. So let's say I'm swinging this thing around. Now I have to move my hand, but imagine my hand's not moving, right? So this is like going in every direction around me, right? So imagine it's just like, wow, but it's tethered. It can't go past this, right? So as it goes around, no matter where it is, it's on a sphere. And so it's like this is all your phi's changing, this is all your theta's changing, and I'm fixing R. So you create the sphere. Just like in cylindrical, when you do that similar thing, you create beer cans, right? Okay. Now, when we use spherical coordinates, our conversions are not as nice as they were in polar and cylindrical. You know, it was just x r cosine theta. Y is r sine theta. Z just stays z. But when you go to spherical, things get nasty, all right? X is now rho, which is the radius, okay? Cosine theta sine phi. Phi, phi. I think I say phi most of the time, but I think you'll hear it both ways. And then y is rho sine theta sine phi. And then z is rho cosine phi. And then this right here is an identity. If you were to take this right here, square it, plus this squared, plus this squared, you would get a bunch of Pythagorean identities, and eventually everything would cancel out, and all you would get was rho squared. So you do have an identity that's similar to polar in this one. You have x squared plus y squared plus z squared equals rho squared. That is an identity you get with spherical. And it makes sense, right? Isn't that the equation of a sphere? Right? So the substitution that we make for x, y, and z should look like a sphere, right? Question or comment?
Sure, can I put this in my notes?
Uh-huh.
Theta would still be the inverse tangent of y over x in this case?
Theta would still be arctangent of...
If you're converting from Cartesian to spherical. Your theta
would be arctangent of y over x in spherical.
Yeah.
I'm almost, okay. I want to say no way, okay, because I'm pretty sure it's no way. I'll double check, but I'm pretty sure it's no way. It's because the geometry, okay, why did we use arctangent and polar? Because when we're doing polar, we're working with the right triangle, aren't we? Like when we were trying to move around, like in the XY plane, you're trying to get to this point, right? So we said, how do we get there? Either give me X or Y, X and Y, or give me an angle and give me a radius. And then from that right triangle, we came up with basically that arctangent of Y over X is theta. But in spherical, your X is not X is not r cosine theta, and Y is not r sine theta. So you don't have the right triangle anymore.
I was thinking, my thought was, if you were to project, so if you were to project when you have an image, you're in the image of the screen showing how you get
Yeah.
coordinates.
Let me bring it back up.
Yes, this.
Okay, let me try and
I thought if you project everything onto the XY plane, theta would still be the same angle, wouldn't it? And your X and Y wouldn't change. I'm thinking of just projecting this onto the XY plane, since Z doesn't have anything to do with theta.
let me look here. Let me take this thing out.
So it's kind of like even if you go out Z, you're still making a right triangle. It's just
I hear
down.
what you're saying, but your X is, okay, here, I think I can explain it. All right, let's go back over here, all right? Phi, right? Okay, theta, right? Theta has an impact on where I am, right?
Yeah.
Rho does, but X, right? How far do I go out? If I give you rho, that's not enough, right? Because rho is like the length of that orange thing. Phi tells me how far I'm going out, right? Just how far do I walk out that way, right? So you have to give me rho, right? And phi. So if phi is really small, your x coordinate is very small, right?
Yeah.
If phi is larger, your x coordinate is further out.
Yes.
And then theta turns me, right?
But your Y coordinate scales just as much as X as you scale theta, as you would increase rho, your X and Y, the ratio between X and Y would stay the same, wouldn't it?
The ratio between x and y?
Yes. And since we're finding the arctangent of that ratio,
Let me consider this a little more. I mean, because really, I've never looked at it. I've never tried to derive. I see what you're saying. Like this is the same scale factor.
maybe I'm just, I don't know. I'll look it up when I'm.
No. This is. I've always perceived x to depend on. Like here, x depends on two things, right? R and theta, right? R and theta. Here, x depends on rho, theta, and phi.
It does, but it's.
No, you know what? Just the algebra on that, it's right there. Man, this makes me excited. This makes me excited.
But could you go like more in depth? Like I don't know if that's like off topic, but like.
Well, we're already off topic, but look at this. If
What if theta's pi over 3 and phi is pi over 6?
hold on,
Or pi over 4?
hold on, Milton, hold on. I guess what I'm trying to figure here is what is tangent of theta, right? What is tangent of theta? I think I want to look at this a little more. I want to look at it right now. I mean, like, I'd like to just continue this, but I'm afraid this might take us too far off.
That was right after this class? Or?
Pardon? I don't have them right after this class. How about if we just solve this for both of these for sine of phi? Solve both of those for sine of phi. And you get x is equal to rho cosine theta should be equal to y over rho sine theta, right? So all I did was solve this for sine phi, which divide here, right? Sine phi divide here, and then set them equal to one another. And the rows cancel, don't they? You just multiply both sides by rho, and then sine theta over cosine theta is y over x, which means that tan theta is y over x, which means arctan theta is, right? That means that theta is arctan of y over x. Wow. Interesting. I don't think the book mentions that.
Yeah, I didn't either. I was thinking of it in my head and like on paper.
That is a very nice observation. Hold on. I want to see if the book mentions it. I don't think it does, though. They don't have.
Well, if you think about it graphically, theta is just the angle made with the xy plane, and then
Mhm.
phi is just the angle made with the xz or the yz plane.
Mm-hmm.
So
Yeah. I mean, I don't see anything wrong in that logic right there. Like the algebra, if these are the substitutions we're making, then that falls out. I'm just curious why books never mention that. And I think I know why. I think it's because you're never really converting from spherical back to Cartesian. Like there's not a major need to go from spherical to Cartesian as much as there is to go from Cartesian to spherical. Like,
That's what I was thinking, was going from Cartesian to spherical, because you need to find theta when you go from Cartesian to spherical, don't you?
no, if you want to go to wait, are you saying,
Going from Cartesian to spherical, you need to find your rho, your theta, and your phi.
if you want to go to Cartesian, you replace all your x's with that, and all your y's with that, and all your z's with
I
that.
was thinking of
That's
comparing them all.
now if you give, yeah, so it would be different if you want to go backwards.
Yeah.
Right? Because like when you look at, yeah, I mean, I would put my definite approval on that. I don't see any problems with that at all. It's just, it's never, I mean, the book doesn't mention it. I don't think I've ever thought about, like, is that the same identity as it is in polar?
I guess it's because rho doesn't change the ratio of x and y.
Yeah, it's this thing. It's this right here. It's that. It's the fact that those are both the same scalar, basically. So if this is basically polar, but scaled by a factor of sine phi. That's really good observation. Right, so I'm excited about the future. You know, you teach this enough and you start to not get, I never get bored with this, but, you know. No, not me, my students. You know, like I want my students to still challenge the material too, so. All right, let's move on. We need to kind of reground ourselves. We're trying to go to spherical. Here are the conversions, right? Here are the conversions. And then let's look at do you remember what the first triple integral we ever did? X was between two constants, Y was between two constants, Z was between two constants, and that was like a box. Let's look at a spherical box.